So we have A plus B plus C equals 1, 7A plus 3B plus 6C equals 7, and then 10A plus 2B plus 5C equals 13. We have these equations, so what we are going to do is that we're going to row reduce. So we're going to collect the coefficients we have here. Okay, so here on the first column, all the coefficients for the letter A, 1, 7, 10. On the second column, coefficients for the letter B, those would be 1, 3, and 2, 1, 3, and 2. On the next column, coefficients for C, 1, 6, and 5, 1, 6, and 5. Then we write an augmented column that contains these values. And we use the row operations. Remember the row operations, 3 elementary operations. You can swap, you can multiply a row by a scalar, and you can multiply a row by a scalar, add that to another row, and then substitute or replace that other row. For example, and so the intention being would be to first create zeros on position 2, 1, and 3, 1. And then create a 0 on position 3, 2. So we'd like to have non-zero, 0 below, non-zero, 0 below, and that number non-zero. That'll be our first goal. Then we need to create other zeros in some other locations. So this is, if you want to do it by hand, this is definitely doable by hand. You could also use something like Sage Math and row reduce this. That's what we're doing, right? But let me just do a few steps here in the row reduction, since they are not such a big deal. The first coefficient on position 1, 1 is 1. So we could create a 0 on position 2, 1 by doing the following. We say minus 7 times row 1 plus row 2, and then substitute row 2. So let me just do that operation. On row 1, when I write here in a different color, what happens, what is the row we obtain by multiplying the original row 1 by negative 7. So this becomes minus 7, minus 7, minus 7, and then minus 7. So if I wanted to add that to row 2, so what we're doing next is creating a new matrix. Every row stays the same. 1, 1, 1, 1. Every row with the exception of the second row. 10, 2, 5, 13. That stays the same. But then we add the new row obtained by multiplying negative 7 times row 1. We add that to the former row 2. There we have minus 7 plus 7. That gives us 0. Minus 7 plus 3 gives us minus 4. Minus 7 plus 6 gives us minus 1. And minus 7 plus 7 gives us 0. So we have successfully created a 0 on position 2, 1. We can easily create a 0 on position 3, 1 by doing something very similar. We can say, look, do minus 10 times row 1 plus row 3, and then substitute that third row. So we're going to keep rows 1 and 2 as they are. 1, 1, 1, 1, 0, minus 4, minus 1, 0. And then we're going to modify row 3, the former row 3, the previous row 3. We're going to multiply row 1 by negative 10. So this gives us minus 10, minus 10, minus 10, and minus 10. And we're adding that to the previous row 3. Minus 10 plus 10 gives us 0. Minus 10 plus 2 gives us minus 8. Minus 10 plus 5 gives us minus 5. Minus 10 plus 13 gives us 3. So in 2 steps with 2 row operations, we have created 2 zeros on positions 2, 1, and 3, 1, this matrix here, this augmented matrix, is row equivalent to the original. This process will continue. And you will find that the reduced row echelon form, by doing this type of operations, is a matrix that looks like this. I'm skipping some of those steps. It's healthy for you to do these steps, okay? But I also need to discuss a couple of other things with you. So by finding that this is the RREF, what we conclude here is that A equals 7/4, B equals 1/4, and C equals -1. So A, B, and C are the numerators on our original proposition that this is the sum of fractions, the so-called method of partial fractions, right? So this would lead us to conclude that, so therefore, big S could be expressed as 7/4 over S plus 1 plus 1/4 over S plus 5 plus -1 over S plus 2. Could write that, let me write that yet again. Big X, this is 7/4, 7/4, times 1 over S plus 1, and then 1/4 times 1 over S plus 5, then minus 1 over S plus 2. So what we would like to do next is the last step on that recipe. You've worked with step 1, take the Laplace transform. Step 2, use initial conditions. Step 3, solve for big X. That part of solving for big X and then using partial fractions, that was the most involved here. Step 4, take the inverse Laplace transform. Excuse me. So we'd like to take the inverse Laplace transform. Inverse Laplace transform, both sides of this expression. The inverse Laplace transform of big X would be little x. This would be little x of t. Here we have 7/4 times Laplace transform of 1 over S plus 1. So that would give us e to the minus 1t. Inverse Laplace transform of 1 over S plus 5 would give us e to the minus 5t. And the last one would lead to e to the minus 2t. So here this is multiplied by 1/4, and this has -1 in front of it. So this is 7/4 e to the minus 1t plus 1/4 e to the minus 5t minus 1 e to the minus 2t. An important thing is for you to verify that this would satisfy the differential equation. So you can differentiate once, differentiate twice, and verify that the differential equation is satisfied. Also, you can verify little x evaluated at 0. It looks like 7/4 times e to the 0 plus 1/4 times e to the 0 minus e to the 0. So this is looking like 8 fourths minus 4 fourths, which is 1. So little x of 0 equals 1, and that's precisely the first initial condition. What happens to the second initial condition? First derivative, let's see, first derivative would be minus 7 fourths e to the minus 1t minus 5 times 1 quarter minus 5 fourths e to the minus 5t, and then minus 2 times minus 1 is positive 2 e to the minus 2t. That's the first derivative. And if we evaluate the first derivative at 0, we're looking at minus 7 fourths times 1 minus 5 fourths times 1 plus 2, which is 8 fourths. So we have minus 12 plus 8 fourths would be minus 4 over 4, which is negative 1. And negative 1 is the other initial condition. The first derivative evaluated at 0 equals negative 1. So the thing that's left here for verification is to compute the second derivative and verify that first and second derivative satisfy the original holiday, higher order linear ordinary differential equation. So that when you add them up with coefficients 1, 6, and 5, you end up with the quantity 3 e to the minus 2t. And that would be the final verification. Right? Based on verification of initial conditions only, we can see that that solution seems to work, seems to be what we want it to be.